Intentional Electromagnetic Interference, or IEMI, Module 8.2. In this module, we specialize on critical infrastructure. What are the special problems associated with IEMI scenario for critical infrastructure protection, and discussion of some mitigation philosophy. IEMI itself is a challenge, and when it is applied to critical infrastructure, it has got several other special issues. Examples of critical infrastructure are electrified railway systems, power grid, communication system, etc. And all these systems are distributed systems spread over large geographical areas, and that itself gives some speciality to it in terms of protection. Main difficulty is how to estimate the vulnerability of such systems. It is very easy to estimate the vulnerability of very small systems that are confined. One can do tests in the lab, or one can inspect and know everything about the system and try to estimate the vulnerability, whereas distributed systems poses a big challenge. One challenge is that it has got several accessible points where malicious electromagnetic energy can be introduced into the system, and often we may not know everything about these accessible points because systems are so complex and distributed. Then we can't restrict access to critical infrastructure often. I mean, to some points we can restrict access, say for example the control center or critical equipments, but otherwise it has to be quite open because people has to use it, like a bank or railway stations, etc. Then locations. Some of the locations where critical infrastructure is present are in remote areas, and you don't have normally any surveillance of those areas, so far off the beaten path. And there the attacker can try several times certain attack strategies, and that becomes a threat. So the anonymity factor is normally not included in the traditional EMC consideration, whereas with critical infrastructure protection in the light of IEMI, that has to be considered. Another difficulty is that it is not possible to make an EM topological boundary into a physical barrier. So this we have seen in the previous chapter. So what is meant by this? This can be illustrated here. Imagine this is a building complex. Well, it is not a critical infrastructure, but suppose that if it is a critical infrastructure, it can be a very important control center, let's say. Then, well, how do we protect this system using the topological zoning concepts? You can have several circles or several layers, let's say, need not be circles. So for example, outside of this building it can be zone 0, where you can have all kinds of disturbances from severe sources. Then that there is a zone boundary from the topological point of view, and any services that is going into or anything that goes into are controlled at this boundary and reduced to zone 1. Then here the EM specification, electromagnetic specification for sources are less severe compared to zone 0, because you have already mitigate or already reduced it, attenuated it with these measures at the boundary between zone 0 and zone 1. Then between zone 1 and 2 again you have some controls, and between zone 2 and 3 you have controls, and by the time it reaches to the most critical and vulnerable part, you have reduced your sources to such a great extent that the protection is realizable. Now imagine the case of IEMI scenario where you don't have a physical barrier between zone 0 and 1. A perpetrator can get inside, can come across the doors and deep into the different zones, EM topological zones, and maybe over here there is a boundary in terms of a locked room or something like that. But the type of disturbance that you find in zone 0 can be suddenly introduced into zone 2, and only one boundary between zone 2 and 3 is now in between, and this may not be adequate. So you are compromising the zone boundaries in the IEMI scenario. So this is a huge challenge. So it is not often certain that one can have any foolproof protection for IEMI in all cases, especially when it comes to critical infrastructure. So often one adopts a strategy of graceful degradation. So here the assumption is that there can be some attacks that is happening that are not always predicted by normal EMC standards or testing. Then when this type of attacks happens, the system will respond, but make sure that system is gracefully degrading. It means that you don't have any catastrophic failure, but system is degrading in a controlled manner, so that still critical functions are going on, and without any catastrophic failure it shuts down or something like that. So this has to be built into the system. So diminishing the consequence of the disturbance may be more viable than the prevention of all consequence. So that is the basic approach that is being taken in the case of IEMI. So it is not the same as just adopting the traditional EMC. It is much more than that. So the concept of degrading gracefully and introducing subsystems or operating procedures to maintain operative status. So you can decide that when a system is under attack and it cannot function normally as it should, at least some basic functionality it should have to keep the most essential part of the system still running. So this has to be built into the system in terms of subsystems and operating procedures. One common example can be backup power for all critical systems like battery, UPS and things like that, with more extended capabilities and automatically kicking in. Then system designing with parallel subsystems. So if one system is disturbed and all, automatically a parallel subsystem that can mimic the function can take into control. And often parallel subsystems are widely employed when it comes to power control centers, because even if one control center is down, then other control centers will take up the same function at geographically separate distance. So this is often there with some of the critical infrastructure systems. So this is another strategy, duplication of the control function. Then operator procedures, how to deal with, there has to be established procedures how to deal with a suspected attack. Then legislation, because when systems are built, economy is something very important, And unless protection against IEMI or those type of rare events are built into the legislature, into the rules, not enough money and resources will be allocated for those protection. So these are the various ways in which critical infrastructure protection can be approached. The mitigation philosophy has the benefit that the protection and improvements performed will also increase the reliability of the system, even for unintentional disturbances. So if you design for IEMI, surely it will have an extremely good design for normal EMC also. So that is a bonus point. Your overall reliability of the system is increased. Now let us look at how we can put this type of philosophy into practice, because it is one thing to know the principles involved, but how do we quantify the systems? Say, for example, how do we evaluate a system and say that, okay, this system is protected against IEMI, or it has certain degree of protection. So this system A is more vulnerable to IEMI than system B, or system C is more hardened than system A and B. So how do we say this kind of things by looking into evaluating a system? So you need some sort of a classification method and quantification of various factors. So that is what is being talked about now in this. So looking at the property and the process of IEMI, one can think of a parameter accessibility. That is how easy to gain physical access to different parts or critical components of a system. Because only when one is having access to physical access, a disturbance can be delivered into the system. So how easy it is. So this is one scenario. So physical access means that it can be for a person, or it can be for a signal also. It can be through some other means. So this need to be evaluated. Second thing is, if there is an interference, what is the consequence? Because there can be systems in which you can have an interference, system is getting damaged or it is getting down, temporary damage, upset, but the consequence may not be great in one system, but similar kind of damage in that subsystem, but when it is used in a critical function, can have much larger consequences. So one need to have a measure for the consequence of interference. Then susceptibility of the system, how susceptible the systems are to certain levels of interference at certain frequencies and all. So here it can be further divided into sub classes. So for example, receptivity to disturbance. You can apply a signal, a transient to a system, but the system may not be receptive to that. So the degree of the facility's ability to mitigate disturbances between and within electromagnetic topological zones. So this is called receptivity, because you have quite good protection, zonal boundaries and all. So that need to be quantified. Then sensitivity, the different upset threshold levels of the equipment and subsystems inside the facility, how sensitive the systems are. Some systems may be too sensitive compared to some others, so this need to be determined. Then redundancy. So even if one system is down, can that function be taken over by another system? And can this be taken over automatically without intervention of human beings? So this redundancy is associated with degrading gracefully. So how do we combine all these three characteristics? So one can think of an intentional electromagnetic interference vulnerability cube. So this is taken from these publications in IEEE EMC. So in this cube you have three accesses. One is the consequence of an attack, and first of all, how accessible the system is, accessibility in one axis. Then how susceptible the system is to the attack. Then what is the consequence of the system being down, or this, what is the consequence of the response of the system to the attack. So these three axes one can quantify and plot. Then suppose if you are in this corner somewhere, then of course system is good. So the accessibility is bad. You don't have, or the accessibility system is not very good for the attackers. Even if it is attacked, the susceptibility of the system is not that great. It is not very susceptible, so it is lower in this axis. And even if something happens, consequences is not great, again lower in the axis. So of course this is the ideal case, but of course no case will be here. It can be that some systems, the type of method being used in protecting the system is, well, make accessibility almost impossible. So if you don't have any accessibility, even if the system is susceptible and the consequence of that susceptibility is high, you are still over here at this corner of the point. Then suppose if the system is not at all susceptible, then you are kind of at this corner over here. So likewise you can consider different corners, and if you can get it somewhere over here, then that may be a fairly good system, somewhere in the middle of the cube if you can get it. So this is just a concept, and each axis has to be determined individually and quantified. Now, an example of investigation of a complex system for the risk of susceptibility to IEMI that is described in the next few slides. So this is taken from this particular thesis, PhD thesis, as well as from this publication in IEEE EMC. Now the system investigated is the European Rail Traffic Management System, ERTMS. And what kind of threat is posed to that system by radiated intentional electromagnetic interference? ERTMS is the upcoming railway signaling system, railway control system that are being deployed in European countries, including Sweden. Already several lines are converted into ERTMS. So in the ERTMS system, you don't have any optical signaling, and you don't have definite blocks. So this will, ERTMS will allow much more denser railway network. It is possible to have, so trains can follow one another within a minute or so, because you have kind of a moving boundaries for the block, moving blocks. and there are no light signals like green, red or amber signals. Instead, everything is controlled by radio communication. So there are equipments within the train facilitating that in terms of several antennas and other things. Then you have on the track also there are several equipments. So in the train you can have speed sensors, and in the track you have balises embedded into the track. The balises will have information on what is happening ahead, whether you have a block that is coming in or where is the next train, and all kinds of information can be there in balises. So they are stationary systems on the track, and balises are normally broken in, turned on into life by an RF wave that is being illuminated into it. Suddenly it wakes up and it releases information to the train, and train will know what has happened. So all these equipments are there, but the most critical thing for this are the communication system between the trains, which uses this trackside antenna, and also to the stations. So these communication systems, so they are called GSMR communication systems, and they are operating at these frequencies, 876 to 915 megahertz and 121 to 960 megahertz for downlink. So these are the communication standards used in Swedish railways for ERTMS now. So the investigation being conducted is that if someone is trying to disturb the communication, how can we evaluate that threat? If someone is aiming at this communication, in tampering with this communication. So the scenario is like this. Suppose some rogue element is coming with a van with a powerful microwave or UWB or HPM sources radiating, then either it can affect the train communication system, the communications antennas mounted on the trains and the equipments in the train, or the trackside stationary antennas on mast. What is more important is trackside, because that is stationary, trains are moving. So this study is presented now. So radiated power, some of them will be attenuated. You have to estimate that, and some of them will be received here. Then it will be transferred to the electronics. So all this, one has to follow all these chains. So we couple it with our standard EMC components. In a system, you can divide into source, victim, coupling path, etc. So this standard figure comes in many contexts. So basically the analysis method is the same, except that regarding the source of investigation, we will take not something that is naturally occurring but in its environment, but something that is intentionally introduced. So we look at what are the available HPM high power microwave, say for example a microwave oven or something like that in the public sector. Classify available HPM and UWB sources after power, type, size and availability, because these are the kind of sources that may be available for perpetrators. Then, so once we know the source and how much power can be delivered to the target, the trackside antenna, so there we look into free space polarization, impedance mismatch losses, ground reflection losses, atmospheric attenuation, system effectiveness, for example aperture efficiency, radiation efficiency, etc. So all these things are brought into picture, then after that, you know that how much the target will be receiving, how much power will be, or how much energy will be available at the receiving antenna. Then of course the receiving antenna has got certain polarization characteristics, and because of that it has got certain gain, and depending upon the incident angle, what is being received can be different. And here one need to be careful for the specification may be this bands, but actual antenna work not only at this band, because the antenna may be optimized to have maximum gain at these bands, but that does not mean that it is not responding to the frequencies outside this band. Of course it will respond to frequencies outside that band also, sometimes as effectively as this band. So even that has to be considered while looking at the frequency spectrum of the wave falling on the receiving antenna. Then losses between antenna and system. So there will be cables from the antenna to the electronics, certain length of the cable, so how much will be lost. So you have to know about the cable characteristics and the pulse propagation along that cable. This can be found either by simulation or by experiments or using manufacturer's data. Then the signals are amplified, the actual signals. So of course the noise also will be amplified. So there is a low noise amplifier susceptibility, low noise amplifier LNA at the input, at the first stage of the electronics, and how these low noise amplifiers, because they are working at several hundreds of megahertz or even bordering on gigahertz, so how this will respond to the transients, the intentional EMI of the characteristic of HPM and UWB. So that need to be tested and see if those low noise amplifier will be destroyed. So this is perhaps the most vulnerable part in the whole chain. So one has to have a very good idea about it. So these are the several steps involved in the investigation. And real systems were tested in anechoic chamber and using other test facilities. And some of the details are given here. So for example, receiving antenna characteristics. So this is the trackside antenna, one example of that. So directivity, gain at different frequency bands, reflection coefficient, significant gain outside the desired GSMR band. So that is kind of backdoor coupling. All these were found out. Attenuation in internal cables between antenna and the communication system, electronics. So the attenuation in three types of cables that are used: low density form coaxial cable with a solid shield, LDF50, then braided shield cables RG223 and RG214, transfer impedance and all these characteristics, attenuation, all these are investigated. Then susceptibility or damage threshold of low noise amplifier, what power is required for destruction of LNA, and whether the signals reaching the LNA is above that value. So this determination has to be made. Maximum threshold separation distance, say for the given source that are available in the public domain, what is the maximum separation distance required not to have destruction to the system. So this should consider polarization, impedance mismatch, angle of illumination, cable losses, ground reflection, etc. When one get into results like that, so what is shown here is the maximum free space separation distance between transmitting source and receiving trackside GSMR antenna to destroy the low noise amplifier, because that is the most sensitive part of the system. For elevation angle and a source with medium power level 1 megawatt. So this may be like a small car mounted or station wagon mounted source. So in this picture, this is the distance between the receiving antenna and the source. This is the elevation angle, at what elevation angle the source need to be. Of course, not all this elevation angle are possible, because practically you are at ground level and the equipment is on a mast, so you have certain angle for the elevation. Then this axis shows the frequency up to 2 gigahertz, and the color coding is for distance in meters. See, you can see 200 meters here, 150 meters, like that, but mostly at zero elevation angle. So you have to have the bore sight. And as elevation angle increases, then you have distances are also changing, and frequency. So this is a very complex picture in 3D, and to get a more easily understandable figure, one can translate that into this. For example, frequency versus elevation angle, and what is shown here in the dark are the critical regions. So when the source is mounted in these regions with respect to the antenna, then you can have disturbances. The critical regions for permanent damage to the trackside antenna when illuminated by a 1 megawatt source, and the transmitter is aiming at the GSMR antenna. So say take the example of say 1.3 gigahertz, the dominant frequency HPM source, let's say. So if the angle made between the receiving antenna and the source is around 40 degree or something like that, you can have trouble over there. But if the distance is in such a way that the angle is beyond that, then you don't have trouble. So likewise, you know that where the van has to be positioned to be a threat to this antenna. So once you know this, you can have physical barriers so that no one can approach the antenna at these vulnerable distances and angles. So this is one way of achieving IEMI, trying to achieve IEMI by doing the system analysis. I mean, achieving EMC in the presence of IEMI, using detailed study of system analysis. You can see that we have used this classical EMC analysis here, so there is nothing new in that. It is only a different way of thinking regarding the source and possibilities of approach of source to the victim that is being introduced. Now, the conclusion from this analysis as published in that publication, small homemade sources of 1 kilowatt, with a high probability one can say that it's not a threat to trackside or train communication system. You may have maximum that can happen is some temporary upset, but anything permanent. Or it requires generators with power specification of the order of megawatt to be able to create the power necessary for permanent damage. So that is much more harder to come by. So the approximate distances from the antenna to the source to cause permanent damage to LNA, low noise amplifier. If it is a small source, one has to come as close as a few meters. So you have to climb up the the tower to be, well, that is not usually possible. If it is a medium source, 1 to 10 megawatt, even from a distance of a few hundred meters, one can have permanent damage. That is along a road that is nearby or approach road. And if it is large, military kind of systems with 1 gigawatt, even from several kilometers, one can do severe damage. So one can clearly have an idea of how to characterize the accessibility to the source from this analysis. And one has also found the susceptibility of the source from this analysis and identifying the critical system, which is the LNA, and we know the threat levels required for that. So this also can be quantified. And of course, consequence is that what is the consequence of train system? Of course, trains can be stopped or the traffic can be completely disrupted. Now, so one can introduce some special protection for this LNA. So normally there are some protection for protecting against noise, or surges, etc. The gas discharge tubes and normal virus trays may not be suitable for protection because GDT sometimes is slow in responding depending upon the rise time of the applied device. And the MOV can have very large parasitic capacitance and inductance that is not suitable. So often diode based limiters are used for this type of protection, but one drawback is its low energy handling capacity. So this is kind of a conclusion from the analysis, and that ends this module. Thank you very much.